5.2, the derivative of a general exponential function. So our exponential function is in this form here, y equals b to the x, okay? So we have some base, b, and that's going to depict how our graph looks. Okay, so if b is greater than 1, so it's going to increase to the right. And if b is like, I call it like a fraction, right? But you can have a fraction greater than 1. So essentially 0 decimal, a number, right? Between 0 and 1, it's going to decrease to the right. Okay, and that's assuming no reflections. Okay, so the derivative of f at x equals b to the x is, so there is an explanation here. As the limit approaches 0, if we had b to the h minus 1 over h, we would get ln b. Okay, and if f at x equals b to the x, then the derivative of f at x equals ln b times b to the x. Okay, so if we take a look at this, we have this function f at x is b to the x. We take b to the x and we rewrite it as it is. And then we ln b it. Okay, so whatever this base is, we write ln of that base. Okay, so that's if the exponent is just x. Now, if the exponent is actually a polynomial, so b to the g at x, okay, so if this is a polynomial, okay, it's kind of the same approach. We would rewrite it as is, okay, so direct rewrite. We would still ln of the base, multiply by ln of whatever the base is, but then we have to chain rule it. So this right here is our chain rule. We would have to take the derivative of g at x and multiply it by g at x. So, do example 1. Determine the derivative of f at x equals 5 to the x. Okay, so f prime at x equals, if we look up here, we have 5 to the x. We just have base to the x. This is not going to be chain rule. So rewrite it, 5 to the x, and then multiply it by ln of the base. The base is 5. Okay, so it's 5 to the x ln 5. We cannot multiply these. Ln 5 is going to punch out a number. 5 to the x is going to follow exponent rules, so we just leave it. Now, likewise, for b, we have f at x equals 5 to the exponent 3x minus 2. If you look, this entire 3x minus 2, that's essentially going to be our g at x. So, if we're finding the derivative, f prime at x, we're going to write the term as it is, 5 to the 3x minus 2. Then we're going to multiply it by ln b, so ln of the base, which is 5. And then we're going to do chain rule, which is, what's the derivative of 3x minus 2? Well, it's just 3. Okay, we can't multiply these two because there's this exponent on there. It's not the same base. So we don't use exponent laws, so we can just leave it like that. Okay, example 2. On January 1st, 1850, the population of Gold Rush Town was 50,000. Okay, so this is a reference point. Okay, so this is likely, and I haven't read the rest yet, but this is likely going to be t equals 0. Okay, it's like the start time. Okay, and the population is 50,000. So we can call this like the population at 0, or we call it P naught, which is like population and then subscript 0, like the 0. Okay, because it's the population at time 0. You're going to see this a lot in university. P subscript 0. So the size of the population since then can be modeled by this function. So that's easy. F at x equals 50,000, 0.98 to the exponent t, where t is the number of years since that January 1st, 1850. Okay, so if we talk about this, this is in the form y equals a b to the t. Okay, a is usually like the initial amount. I mean, as long as there's not a shift up and down. Okay, b is the base, and t is the time, usually in years. Okay, this is fundamentally how we create an exponential function. So, what was the population of Gold Rush Town on January 1st, 1900? So, for A, let's do this in blue. January 1st, 1900. So, January to January, I'm going to kind of disregard this. So, we're going from 1900. Our starting point was 1850. So, this is 50 years. Okay, so simply working with the original function, because this is just asking for the population. Okay, so it's going to be 50,000, 0.98 to the exponent 50. Okay. So then we just get out our calculators and we solve for it. 18,208. Okay, there are decimals. It's decimal 484. So I'm actually going to leave it because when I talk about population, I just kind of want whole numbers because people can't come in non-whole numbers. So therefore, population on January 1st, 1900 was 18,208 people. Okay, and I'm going to put people because that's the rate, like that's the units. Now B, at what rate was the population of Gold Rush Town changing? So we're looking for the rate of change, okay, on January 1st, 1990. And then was it increasing or decreasing? Okay, so first of all, let's take the derivative. Okay, whenever we see rate and changing, we're taking derivative. So the derivative f prime at x equals, okay, so we're going to treat this 50,000 like a constant. So we're going to do 50,000. And then if you want to see the math behind it, then we're going to take d by dx or d by dt. This should be a t. I apologize. Okay, we're going to be d by dt of the 0.98 to the exponent t. Okay, because remember, this is constant rule. We're leaving the 50,000 out front. It's kind of like a common factor, right? It's just a constant out front. So let's go ahead and do d by dt of 0.98 to the exponent t. So when dealing with an exponential function, we're going to rewrite it as it is. And then we're going to multiply it by ln of the base, 0.98. Okay, so this is the rate of change. So we can say rate of change, okay, on that date. And now we want to know, are we increasing or decreasing on this date? Okay, so if we were to say f prime at 50, right, it's 50 years, is 50,000 times 0.98 to the exponent t, which is 50. This t doesn't look up enough. I'm going to put it more here. Okay, times ln of 0.98. All we're doing is subbing in this 50 because then it's going to give us, it's just like us doing our chart and seeing if this rate of change is positive or negative. Remember, positive is increasing, negative is decreasing. Okay, so putting this into our calculators, 50,000 times 0.98 is the exponent 50 times ln of 0.98, all in the calculator. I get that at this time, it's negative 360, I'm rounding, 8 people. Okay, the population is changing and it's becoming 368 people less. Okay, so therefore at 50 years, or you can use January 1st, 1990, okay, the rate of change was, and then we can say 50,000 times 0.98 to the t times ln 0.98. While they, let's say while the population was decreasing by 368 people. Okay, and it's not per year, but it's like instantaneously at that time. Okay, and just one more connection. This is a negative number. We have to include this. By me writing decreasing, I've included that that number is negative.